finding these polynomials is not like a super trivial, I'm done in like 20 seconds proposition, right? Some of these could take you a little while, especially, listen please. I want you to think about, like if we did change the centering point to c equals 0, those derivatives would go from this to this to this to this pretty fast. They'd be like kind of spiraling out of control product rules. Just get larger and larger and larger with chain rules in there too. So maybe you can identify with the idea that if you've got like a mildly complicated function, even like number 3 kind of sorta, if you're going to do like a 4 non-zero or 5th degree or whatever it happens to be, it's going to take you a while. So you're not going to see a ton of those. It's not going to be some AP test with like, hey, there were 11 questions where it said, hey, construct an original Taylor series, blah, 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 like you did up here. It's just going to take too long. There's just not enough time. And so a question like number 5 is a nice way to assess, do you know how to make a Taylor or a Maclaurin series, a polynomial, without making you write the whole thing out, without making you construct an original one. So just know that this is not an AP question, but it easily could be some multiple choice question, just because it's efficient time. So check it out. See if you can handle number 5. It's kind of backwards from what you just did, but it's the same concept. That's a nice trick for a lip moisturizer.
I think that's what Carmex does, yeah. And it feels like good. Because there's like chemicals.
You don't get insurance.
You see like the instant feel good with the
How do you know? Yeah, Carmex, yeah.
That sounds like the concept of irritated.
More stitches, less ridges.
Yeah, which like, I don't know, my wife has some little studies on it. It doesn't taste very good. So I tried to like, well, if you want this sticky stuff on there.
I get like once, I get that like once every few months because I just like really good.
They said that.
That's cute.
I was a smooth, like I just.
It just gets so bad.
And Aquaphor is not cheap. That's not cheap stuff. Yeah. Okay, let's see what this might look like. Got a couple of questions for you first. So I called this a Taylor series. Can anybody tell me what the centering point is for this Taylor series?
0.
How can you tell that it's 0?
Because there's no. Because of the way it is.
It's just the nature of the beast, right?
That's just the way
Because it's.
If it was centered, listen, if it was centered somewhere else besides 0, what would it look like?
That.
X minus something.
Yeah.
Yeah, it'd be, all the x's would be x minus 5 and x minus 5 or whatever the centering number was. So this is a Taylor series centered at c equals 0. So what would be another name we could call this?
Maclaurin.
Okay, there we go. So then what I would look at here is I would look at the basic construction of one of these Taylor series centered at 0 would look like this. It would be g of 0 plus g prime of 0 times x plus g double prime of 0 times x squared over 2 factorial. Does that make sense? And then it turns into kind of a matching game, right? You'd say, I'm looking for the value of my second derivative at 0. So let's see here. There's that. Which term does that go with? Well, not that one. Not that one. Oh, look, x squared, x squared. Well, that must go with this term, right? So what you could then say is that g double prime of 0 over 2 factorial must equal 3/5, right? That's the complete coefficient is 3/5, and the other complete coefficient is g double prime of 0 over 2 factorial. So you set them equal to each other, and obviously from here the algebra is, for you all, insultingly easy. G double prime of 0 must equal 6/5, right? You multiply both sides by 2. Any questions? Okay, let me present to you a conflicting question. What if I gave you the exact same setup, But instead of saying, what is the value of g double prime of 0? What if I said, what is the value of g double prime of 1? What would you say?
I don't know.
Why don't you know?
Because you don't have C values. You don't have a function? You don't.
So I may or may, well, I certainly don't have a function. You're right about that. So let's see here. Somebody said something about the centering value. Where is our series, our original polynomial centered at? 0. And I asked you about g double prime of?
0.
Well, I did ask you about g double prime of 0, but I just asked you about g double prime of 1, right? So here's the deal. Here's the big concept to take away. A power series, like a Taylor polynomial, Taylor series like this, will be exactly representative of whatever the original function was at the centering point. Exactly. However, once you move even one little smidge off the centering point, all the numbers are different. All of them. Does that make sense? So later on, we're going to be able to quantify, we're going to be able to bound just how different they would be. But for now, all we're going to say is they're different. So if I give you a Taylor polynomial centered at 0, and then I ask you information about what's going on at 1, you really can't answer that question other than to say, if I did, here's how bad it would be. Here's how bad the approximation would be. Make sense? One more thing to think about here. Check this out. I don't know if any of you did this. We still don't have a clue what the function is. It doesn't really matter. Check this out. If I took 7 plus x over 2 plus 3x squared over 5, and I differentiated it, let's see what would happen. The derivative of 7 is 0. The derivative of x over 2 is 1/2. And the derivative of the last term is 6/5 x. That's the first derivative, right? What's the second derivative?
6/5.
So in other words, the second derivative of the Taylor polynomial is exactly the same as the second derivative of whatever the original function was at 0, right? If I move off of 0, they're different. But since it was centered at 0 and I asked you about 0, they're the same. That's only true at the centering point. If you move off of it, no longer true. Make sense?
So if the function you're given doesn't have an x minus c value, you can just assume that it's centered at 0?
You don't even have to assume. Like, that's conclusive evidence that it's x minus 0 technically. So yeah, that's definitely something you want to be able to recognize. And by the way, I'm never going to do the jack here and expand things out and be like, hey, guess what the centering point was? Good luck. Never going to do that to you. I'll leave it unsimplified, kind of like you guys had originally there. So, okay. Any other questions? Okay, so let's close off our class with a couple of other examples similar to what you've been doing at the start of class. These are both lovely and very important. I'll tell you what, I would like for you guys to do number 7 first. Let's do 7. And if we have time for 6, we'll do that. I think there's a cool connection, and I think I have this timed more or less right for us to do this. So number 7 says, write the first 4 non-zero terms and the general term, the Taylor polynomial for f of x equals 1 over 1 minus x. This might seem super random. Like, you probably understand why we would be concerned about sine or cosine or e, like in number 6. Why would we care about some random function like 1 over 1 minus x? So like the nth term, like the pattern setter. For number 7, I think it'll be pretty apparent. If you do it right, it'll be pretty apparent what it is. Oh, you know what? I probably should have written Maclaurin. C is 0. I want you to do 0. Sorry about that. We're just going to call that a typo. So here we go. Do this. Do a Maclaurin polynomial. So it's Maclaurin. See if we can figure out what this is. You might be able to see a pattern pretty quickly. So I wrote some derivatives up there. I just wrote the first three derivatives. If I want to compare. So like notice on all my derivatives, there's like a times -1 on all of them. That's that changeable derivative of the side on the inside. I think that's where you're.
Where did all your numbers go?
Where did all your numbers
I'm seeing some changeable issues on derivatives. Be careful that you multiply by the derivative of the inside. So we actually, this is discussing this a little bit. So there definitely is a domain.
Great question. I think it's supposed to make the summation of it.
Josh, you're right.
Oh,
We're gonna do this one.
you know how general form is supposed to be?
We're not gonna really.
Yeah,
do
it's
that
like
yet.
really derivative of the-
It's hard series of things for us to do it to
I don't think about it.
actually.
Like the second derivative
It
is
works really well, but only for this
derivative is
neighborhood.
6. Fourth derivative is 24.
So,
And the creator.
you're right.
Oh, no, it just says right, the first four non-zero terms and the general term.
Yeah, but like that's the pattern.
Oh, I'm not supposed to write like summation.
Bless you.
Maybe. I thought you were just talking about the pattern. What you would describe.
Do what? General
So
term?
am I right here, or do I go
I did a summation like that.
so like with the general term thing?
What is the general term? Is that the?
It's like the nth term, where you
Is it like-
figure out what the pattern is.
Like the infinite summation, is that how you want?
No, I would just, I mean, depending on how you note it, I suppose you could get into a little bit of trouble. If I'm looking for an nth term, I'm basically would just be looking for the element within the sigma,
Okay.
right? Like the thing that's actually being added up.
Okay.
If you wanted to throw a sigma in there, I'd put the sigma at the start and say, hey, sigma from I equals whatever to whatever, probably, 1 to infinity, I'd imagine, of that, and then equals, and I'd stretch out all the terms in the series.
Yeah.
Um,
That makes sense.
yeah.
Well, when I had this, I started it.
Okay, so I've kind of added another chapter to this. I've constructed the Maclaurin polynomial. There's a little simplifying that I would like to do here in a minute, but how you guys doing? Are you okay with your derivatives? Any questions so far? I'll write the simplified version. This is where this starts to get kind of cool. And maybe you notice that if you kept doing derivatives, wouldn't each successive derivative just bring like the next number in the upcoming factorial down to the front? Like the next denominator would be 4 factorial, but do you see how a 4 would come down in the front and cancel out with that new part of the factorial? So you're going to get a cancellation between the coefficient on the top and the factorial on the bottom every single time. So did anybody come up with an nth term? And I would note the nth term like this, plus ... plus what? X to the n, yep. We don't have to put a sigma in here. Like when you write your nth term, you don't have to specify where did my n start, right? You don't have to say, hey, if you have to start it at 2 or 1 or 0 or whatever. Basically write it in such a way that it fits your pattern. And write it in such a way that if I looked at it and said, hey, look at, they started at 0, it all makes sense. Or they started at 1. And if you want to be really weird and annoying, you could say, well, you know what, I started my n at 10 trillion and 6. And so that's why there's always like some folks that are like, I'm going to try to be as annoying as possible and like start my n's at weird spots. Start them at like 0s and 1s and maybe 2s or something, whatever's appropriate. You doing okay with this?
Yes.
Let me take it all the way back to the start here. Why on earth would we study cosine? I think that makes sense. It's fairly unique and interesting. Why would we study sine? Cool. Why would we study e to the x? Very important number. What on earth is so urgently important about that? Comes down, certainly there is a relationship with natural log there, for sure. But there's something else, and it's over here. So these questions, do you recognize this function in series pattern? Maybe you do, maybe you don't. Another one I think is really important that might help you with that. Why do you think that this polynomial only represents this function for that specific domain, -1 to 1? Any thoughts? If you can put these two questions together, you'll be able to see this. And it's something you've seen a lot, actually, in the last month or so. You'll recognize that polynomial, the series pattern. 1 plus x squared plus x cubed plus x to the fourth plus ... x to the n equals 1 over 1 minus x. It's geometric, Jordan. Yes. There's always somebody that sees this. If you're not seeing it, check this out. What if I rewrote this like this? If we replace the x with an r, what might the r stand for? Common ratio, right? And you remember how the sum of a geometric series is equivalent to first term over 1 minus r? Check it out. Isn't that what this is? If you start the series off at 0, the first term's 1, right? Divided by 1 minus the common ratio. It's the geometric series. So then why on earth would this series represent this function only on that domain -1 to 1?
Because the geometric series R has to be between, the absolute value has to be between 0 and 1.
That's right. So x is the common ratio. Its absolute value has to be between 0 and 1. Or, of course, you could say -1 to 1 if you drop the absolute values. That's exactly right. Isn't that lovely? Isn't that cool? Nice job, Jordan. That actually might set a record for fastest to recognize. Sometimes we sit here for like 10 minutes. I don't know. Good job. Okay, so hopefully cool connection for you. Any questions on that one at all? We're going to wrap up our class here in a second. Yeah, Liz.
So where does that -1 come from in the derivatives?
Chain rule. So we got to multiply by the derivative of the inside.
Oh.
The inside's 1 minus x.
Okay.
So yeah, each time you're going to get that -1, which changes everything over to being positive is the key there. Yeah. All right, so we'll handle E next time, and next time we'll also handle what I think might be like the most intimidating looking notation of the year, the Lagrange error bound. It's not that bad. It's really not. We'll deal with that next time. So hope you guys have a good day. See you tomorrow.